So here we go. This is how Bass Strait looks like between Victoria and Tasmania. It is a relatively shallow strait. We call regions like this. Okay? A strait that connects deeper oceanic basins. Okay, relatively shallow. It's only 60 to 80 meters in the center. Let me switch on the pointer here. 60 to 80 meters in the center, and at both sides, even shallower sills, we call them, sill region. Okay? On one side here, less than 40 meters on the other side. The general circulation, the currents of the region are shown in the other graph. You can see here these currents. So you have currents which are generally tend to come from west, flow from west to east. Okay, you have some flows which go into the opposite direction, some countercurrents, but generally you have a water flow from west to east. Okay, and then there is we call it the Bass Strait Cascade. This is an outflow of dense water in there. Anyway, so this is a wind-driven circulation, generally flowing from west to east. So now what you can do that you develop a numerical model. Okay, a hydrodynamic model, and you calibrate this model. Okay, and I'm not going into the details with that. And not going into the details is the tricky field of geophysical fluid dynamics. Okay, if you want to learn about that, I can give you some learning material. Okay, and then once you have developed that model, you can add a concentration field to it. And this is shown here on the next slide. So what's done here is that Bass Strait is filled with a tracer of concentration of 1. 1 is equivalent to 100%. And the starting point here is 1 month after the release of your tracer in June. Okay, so this is a typical June situation where the red is the tracer. You can see you actually have two connections to the ambient ocean. One is on the left, on the western side. You look from above indeed here, and one is on the right. And you can already see here in the first month of the simulation there are some interesting interactions. You can see some eddies here. Okay? This type of thing. And then you go June, July, August. This is the concentration, and you can see that in Bass Strait the concentration decreases, and in some parts it decreases much quicker. Okay, you can see these are the regions where you have an inflow. Okay, in August, for example, you can see this tongue of blue means low concentrations. Dark blue is 0%, is water coming in. Indeed, this is only a theoretical concept. It's like you have a big pot of color and you put it all into a Bass Strait. Okay, this is just a mind experiment. Okay, and then over time you can see that the entire region turns more into blue, and blue means low concentrations. Okay, and you can see the flow. You can also identify regions which have still after 6 months have the highest remnant tracer concentration. Here in November, okay, you can see areas which still have concentrations exceeding 60%. So 60% of the original water is still in these areas. Okay, so these areas are regions of slow flushing, regions where if you have an oil spill in this area, it is much harder, because that water stays in here much longer. Much harder to manage. Okay, and then based on this, you can now record the flushing times. For each area, how long did it take for the tracer concentration to drop to a concentration of 4.7%, which is sort of here in the dark end, and you can create a map, and this is the map. This is the map of flushing times, okay, for Bass Strait, and this is one of my PhD students who did that, Paul Sandry, in his PhD work. Okay, and this is the concentration. The colors are a little bit weird to see, and the longest times are in white. Okay, and you can see how long it takes. 160 days in this area here, and along the northern, the Victorian coast, it's much faster flushing. It's 100 days or so. This is what we call flushing time. Okay, it gives you really detailed information on which areas are flushed rapidly, okay, and which are more isolated from external influences. I show you another example.